Behind locked security doors and beneath endless rows of blinking servers, billions of digital requests move through these facilities every single second. You cannot see them from the road. No signs mark their presence. Some sit in the middle of vast desert plains. Others occupy the edges of northern coastlines where the cold air is used as a resource rather than endured as a climate. From the outside, they appear to be nothing more than enormous, featureless buildings surrounded by fences and camera towers. From the inside, they are among the most technologically complex structures ever built by human hands. These are the machines behind the modern world. Not the phones in your pocket or the screens on your desk, but the physical infrastructure that makes those devices meaningful. The cables, the racks, the chillers, the generators, the cooling towers, the fiber runs, the power substations, the redundant networks, the silent automated systems that never sleep and never stop. These facilities do not take breaks. They do not shut down for holidays. They do not tolerate even a fraction of a second of unplanned downtime without triggering cascading alarm systems that wake engineers from their beds in the middle of the night. What happens inside these buildings shapes nearly every part of modern life. Every financial transaction processed digitally, every streamed film, every search result, every social update, every medical record retrieved by a doctor, every satellite navigation command, every automated industrial process, every weather model, every mapping query, every online purchase, every encrypted message, every cloud backup, every live broadcast, every gaming session, every database query from a hospital system or an airline or a government agency, all of it passes through places like this. The scale is so vast that most people never stop to consider where it all actually happens. The answer is always the same. It happens here. It happens. The demand that feeds these facilities has been growing for decades, and it has never once reversed. In the early days of networked computing, the infrastructure required to support global communications was modest by comparison. A few interconnected university systems, early commercial nodes, government networks designed for resilience during crisis. These were the ancestors of what now spans every continent on Earth. But the underlying logic was always the same. Information needed a place to live. Data needed a home. And as more information was created and more people needed access to it, that home needed to grow. It grew slowly at first, then quickly, then explosively. The emergence of consumer internet access in the 1990s meant that ordinary households were suddenly generating and consuming data. The arrival of broadband in the 2000s multiplied that demand by an order of magnitude. The shift to mobile computing in the following decade multiplied it again. And then came the era of continuous connectivity, streaming services, cloud storage, remote work, digital-first commerce, real-time financial systems, global social platforms, and the demand became something almost geological in its weight and scale. An unstoppable accumulation of digital need pressing against physical infrastructure that had to be built fast enough to keep pace. Today, the volume of data generated, transmitted, and stored globally every single day is measured in units that would have seemed fictional not long ago. The numbers are almost incomprehensible when written down. Hundreds of millions of emails, billions of messages, trillions of individual data packets moving across undersea fiber cables that span ocean floors. And every bit of it, at some point along its journey, passes through a facility like the ones we are entering now. A modern hyperscale data center is not a building in the traditional sense. It is closer to an industrial campus. These facilities routinely span hundreds of thousands of square feet under a single roof, and the largest among them spread across multiple interconnected structures on sites that occupy dozens of acres of land. When you approach one of these campuses for the first time, the scale registers slowly. The buildings seem large from a distance. They seem larger as you get closer, and by the time you are standing beneath the exterior walls and looking up at the rows of industrial ventilation equipment lined along the rooftop, it becomes clear that you are dealing with something in an entirely different category from ordinary construction. Security begins before you reach the perimeter. The approach roads to major facilities are designed to eliminate opportunities for high-speed vehicle threats. Reinforced barriers and engineered chicanes force slow approach. Surveillance cameras observe every angle. Before any vehicle reaches the main gate, it has already been recorded multiple times from multiple positions. Access control at the perimeter requires credentials that change regularly, and the physical infrastructure of the fence lines themselves is hardened far beyond what normal commercial properties would require. Inside the outer perimeter, additional layers of access control govern movement through the campus. Man-traps, small chambers where a person must be authenticated before the interior door will open. Prevent tailgating and force individual credentialing at key transition points. Biometric readers supplement traditional keycard systems. Every entry point is logged. Every movement through the facility is traceable. The people who work inside these buildings know that even a momentary lapse in access discipline can have consequences that ripple far beyond the immediate moment. The interior of the facility is divided into zones, and movement between zones requires passing through additional security layers. The most sensitive zones, the ones containing the densest concentrations of active computing hardware, are the most difficult to reach. Not because the distance is great, but because the number of authentication steps required creates a kind of enforced deliberateness. You cannot rush into these spaces. The systems will not allow it. And then you walk through the final door, and the scale of what lies inside is simply extraordinary. The server hall of a major hyperscale facility is one of the most visually striking industrial environments on Earth. Imagine a space so large that the far wall is genuinely difficult to see clearly. Imagine that within that space, from floor to ceiling, and from wall to wall, there are rows of metal racks stretching away in parallel lines that seem to converge in the distance, like train tracks approaching a horizon. Every rack is densely packed with computing hardware, server units stacked in thin horizontal slabs, each one bristling with cable connections, indicator lights, and ventilation slots. The indicator lights create a visual environment unlike anything in ordinary experience. Amber, green, blue, and white LEDs blink and pulse in patterns that are individually meaningless, but collectively feel like a kind of digital breathing. The rhythm is irregular and dense. Thousands of small lights shifting their states at different intervals create a visual texture that moves and shimmers across the entire length of the hall. At certain angles, under the precise quality of light inside these spaces, the effect is genuinely beautiful. A kind of industrial aurora created by the operational states of millions of individual hardware components. The cables are almost impossible to process individually. Behind and between the racks, in the overhead cable management systems, and beneath raised floor panels, the volume of cabling is staggering. Fiber optic runs, copper Ethernet cables, power cables, management cables, each carefully routed and labeled according to documentation systems that track every connection point in the facility. The color coding of the cables follows conventions developed over decades of data center engineering. Orange typically designates fiber optic connections. Blue marks certain categories of copper Ethernet runs. Other colors identify power circuits, management networks, out-of-band access systems. If you know the code, you can read the infrastructure. The sound inside the server hall is a constant, enveloping presence. It is not one sound, but thousands of sounds, all occurring simultaneously and all in the middle to high-frequency range. Each server unit contains one or more cooling fans. In a large hall, you might be standing within range of tens of thousands of fans running at operational speeds. The combined effect is a roar. not sharp or unpleasant, but genuinely loud. Ear protection is mandatory in many facilities. Engineers who work in these spaces regularly develop a kind of ambient awareness, an ability to notice changes in the sound environment that might indicate a failing fan or an overheating component, even against the background of the broader industrial noise. Every server unit in these racks is performing computational work. The nature of that work varies depending on the function the rack is serving. Some sections of the hall are dedicated to storage systems, dense arrays of drives holding vast quantities of data that must be quickly accessible. Other sections host compute hardware running virtualized workloads for cloud customers. Entire zones might be dedicated to network infrastructure, the switches, routers, and load balancers that manage the flow of traffic into, through, and out of the facility. And in the most advanced facilities, dedicated sections house hardware specifically designed for the enormous computational demands of training and running large-scale artificial intelligence systems. The server units themselves are not what most people picture when they imagine computers. They bear no resemblance to the towers or laptops of everyday experience. A data center server is a flat, horizontally oriented device designed to be mounted in a rack alongside many others of its kind. Standard rack units are measured in a height increment called a U, where 1 U equals approximately 44 millimeters. A single rack typically holds 40 to 48 U of equipment. A 1U server is a thin, wide slab, perhaps 4 centimeters tall, that slides into position on rails within the rack. A 2U server occupies twice that height. Inside each server, the design philosophy is one of aggressive density and thermal management. Processors, central processing units, and, increasingly, graphical processing units repurposed for general computation are mounted on dense circuit boards alongside memory modules and storage interfaces. The physical layout of every component is chosen to optimize airflow. Cold air enters from the front of the server and warm air exits from the rear. The racks themselves are oriented so that their fronts all face a common cold air aisle, and their rears all face a common hot air aisle. This arrangement, known as hot aisle and cold aisle containment, is fundamental to the thermal design of modern data centers. Managing heat is not a secondary concern in these facilities. It is perhaps the defining engineering challenge of the entire operation. Computing hardware generates heat as an unavoidable byproduct of its operation. Every calculation performed by a processor, every bit written to memory, every signal transmitted along a circuit, each of these operations dissipates a tiny amount of energy as heat. Individually, the amounts are infinitesimally small. But when you multiply those tiny heat contributions by the number of operations being performed simultaneously across thousands of servers, the total thermal output becomes enormous. A single, fully loaded server rack can generate between 5 and 15 kilowatts of heat, depending on the hardware configuration. In a large facility hosting thousands of racks, the combined heat load reaches into the megawatts. Removing that heat from the environment, and doing so reliably and efficiently enough to maintain the precise temperature ranges that computing hardware requires, demands industrial systems of considerable sophistication and scale. The cooling systems in a major data center represent some of the most advanced thermal engineering deployed at industrial scale anywhere in the world. The general approach to cooling has evolved significantly over the decades as computing density has increased, but the fundamental challenge remains the same. Cold air in, hot air out, with enough precision and reliability that hardware never approaches thermal limits even during peak load conditions. In earlier generations of data centers, the primary cooling approach relied on large computer room air conditioning units, CRAC units, positioned throughout the server hall to blow cold air into the space and return warm air to the refrigerant-based cooling circuit. These systems worked adequately for the hardware densities of their time, but as servers became more powerful and racks became denser, traditional room-level cooling began to fall short. Modern facilities employ layered cooling architectures that combine room level, row level, and in some cases rack level thermal management. The room level systems establish a baseline thermal environment. Row level cooling units positioned at the ends of racks or integrated into the aisle containment structures provide targeted cooling for high density sections of the floor. And in the most advanced deployments, liquid cooling systems are installed within or adjacent to individual racks to handle the heat output of the densest and most power-hungry hardware. The mechanical rooms supporting the cooling systems are industrial environments in their own right. Enormous air handling units, each the size of a small house, move vast volumes of conditioned air through the facility. Chiller systems, either water-cooled or air-cooled depending on local conditions and design choices, remove heat from water loops that circulate through the building, transferring that heat either to the outdoor environment or to additional cooling systems further up the chain. The pumps that move chilled water through the building are large enough that the piping infrastructure connecting them resembles the kind of systems you might find in a small municipal water treatment facility. Some facilities in cooler climates take advantage of outdoor air temperature to reduce the mechanical cooling load. In locations where the ambient air temperature is reliably cold enough for significant portions of the year, economizer systems can route outdoor air through filtration and humidity conditioning before introducing it to the server environment. This approach, called free cooling, when the outdoor conditions allow the mechanical chillers to be partially or fully bypassed, can dramatically reduce the energy consumed by cooling operations. Facilities in Scandinavia, Iceland, and other northern regions were among the early adopters of this approach, and their success with it influenced the thinking of data center designers globally. Liquid cooling represents the frontier of thermal management in the highest density computing environments. The underlying principle is straightforward. Water, or a more sophisticated engineered coolant, absorbs heat far more efficiently than air. A given volume of water can carry away many times the heat energy that the same volume of air can manage. For hardware that generates concentrated heat, loads too intense for air-cooled solutions, liquid cooling is not merely an option, but a practical necessity. Several architectures for liquid cooling have been developed and refined. Rear door heat exchangers attach to the back of server racks and use water-cooled panels to capture heat, leaving the servers before it can mix with room air. Direct liquid cooling systems route coolant directly to cold plates mounted on the processors and other high heat components, bypassing the air cooling loop almost entirely for the most critical thermal loads. And immersion cooling systems take the most radical approach, submerging entire server units in engineered dielectric fluids that conduct heat away from the hardware directly without any air circulation at all. Immersion cooling facilities have a quality that is genuinely surreal when encountered for the first time. Instead of racks of air-cooled servers lined up in hot and cold aisles, immersion facilities contain rows of tanks, large rectangular vessels filled with clear or slightly tinted liquid. Submerged within that liquid, visible through the transparent walls of the tanks, are the servers themselves. The circuitry is exposed. The cooling fans have been removed. In liquid environments, they serve no purpose. The hardware sits motionless in the fluid while the coolant circulates around it, drawing away heat with efficiency that no air system can match. The engineering advantages of immersion cooling are significant. Hardware can be pushed to higher operational densities. Cooling energy consumption drops substantially. The acoustic environment changes completely. Without the roar of tens of thousands of cooling fans, immersion facilities are comparatively quiet. And the exposure of hardware to the stable thermal environment of liquid cooling can extend operational lifespans in ways that air-cooled environments cannot replicate. The challenges of immersion systems are also real. Specialized fluids, modified hardware configurations, more complex servicing procedures. But as computing density requirements continue to climb, immersion and other advanced liquid cooling approaches are moving from experimental to mainstream. the electrical infrastructure of a large data center is equally impressive in scale. These facilities consume electrical power in quantities that place them among the largest individual power consumers in their regions. A hyperscale campus drawing several hundred megawatts of power is not unusual. The electrical systems required to receive, condition, transform, distribute, and back up that power involve layers of infrastructure that begin outside the property line and extend through every circuit in the building. Electrical power typically arrives at the facility through dedicated high-voltage transmission lines, running directly from substations that may have been built or upgraded specifically to serve the facility's needs. The relationship between large data center operators and the regional electrical grid is substantial enough that new campuses are sometimes negotiated alongside infrastructure investment agreements with grid operators. The facility needs reliable, high-quality power. The grid operator gains a consistent large load customer. The arrangement, where it works well, benefits both parties. At the facility boundary, incoming high-voltage power is received by large transformers that step it down to distribution voltages appropriate for the internal systems. Multiple independent power feeds are standard. Facilities that can receive power from two or more independent substations or transmission paths have a redundancy that allows them to maintain operations even if one supply is interrupted. The risk of losing a single transmission path is real enough, historically, that spending heavily on independent redundant supplies is considered basic due diligence. Inside the facility, power distribution follows an architecture designed around the concept of eliminating single points of failure. The main switchgear distributes power to parallel paths. Uninterruptible power supply systems, massive banks of electronics and batteries, sit in the path between incoming utility power and the server loads. These UPS systems serve a critical function. The time between a utility power disruption and the startup of backup generation is measured in seconds. But for computing hardware that relies on stable continuous power, even a fraction of a second of interruption can cause failures that take much longer to recover from. The UPS systems bridge that gap, supplying power seamlessly from stored energy while the generators come online. The batteries in a modern data center UPS installation are industrial components on a scale far removed from the batteries in everyday consumer electronics. Large valve-regulated lead-acid battery strings, or increasingly lithium-ion battery systems engineered for stationary power backup, occupy dedicated rooms that may run for hundreds of feet along the walls of the electrical infrastructure wing. The management systems monitoring these batteries track individual cell conditions, temperatures, charge states, and discharge characteristics in real time. Battery degradation over time is predictable and managed through replacement schedules that cycle out aging battery strings before they can become liabilities. The backup generators that provide sustained power during utility outages are among the most visible pieces of infrastructure on a data center campus. These are not the portable generators used during camping trips or home power outages. They are permanent, industrial-scale diesel generators occupying dedicated enclosures that may be larger than most residential homes. A large facility will have multiple generators, often enough to supply 100% of the facility's power load from generator capacity alone, with additional units held in reserve. The generators are connected to large fuel storage systems capable of sustaining operations for days without resupply. Testing is a routine part of generator operations. These systems must be ready to assume full facility load within seconds of a utility power loss. Planned test scenarios where the utility supply is intentionally interrupted under controlled conditions to verify the response of the generator systems, and the UPS handover are conducted regularly. The results of these tests are documented, analyzed, and used to improve response procedures and identify any components that may need attention before they cause an unplanned failure. The network infrastructure that moves data through these facilities and between them and the wider internet is a discipline entirely separate from the power and cooling concerns, though no less complex. The physical layer of network infrastructure inside a data center consists of thousands of individual connections. Fiber optic cables linking servers to switches, switches to aggregation layers to core routers, and core routers to the exterior connections that carry traffic to and from the facility. The switches and routers that form the internal network fabric of a major facility handle traffic volumes measured in terabits per second, trillions of bits moving through the network every second. Modern network hardware has evolved to handle these volumes through a combination of high-bandwidth individual connections, sophisticated traffic management software, and physical architectures that minimize the number of hops data must traverse between its source and destination within the building. The network architecture inside a hyperscale facility is typically described in terms of layers. At the bottom of the hierarchy are the top-of-rack switches that aggregate the connections from the individual servers in a rack and present them to the next layer up. Above those are aggregation switches that consolidate traffic from groups of racks and route it toward the core of the network. At the top is the core switching layer, the highest capacity network hardware in the facility, which manages traffic between different sections of the building and interfaces with the external network connections. The physical fiber infrastructure connecting all of these elements is enormous in volume. Fiber optic cabling offers advantages over copper connections at data center scale: lighter weight, smaller diameter, immunity to electromagnetic interference, and the ability to carry signals over much longer distances without degradation. Modern fiber optic transceivers can operate at speeds of 100 gigabits per second or more on a single optical fiber pair, and the density of connections in major facilities means that even at these speeds, the aggregate bandwidth requirements demand vast numbers of individual fiber runs. The connections that link data centers to the broader internet are the arteries of the global information infrastructure. Major facilities have direct connections to internet exchange points, neutral physical locations where different networks interconnect to exchange traffic. They also have direct private interconnections with major content delivery networks, telecommunications carriers, and other large-scale network operators. The bandwidth of these external connections is staggering, and it grows continuously as traffic volumes increase year over year. Underlying all of this is the physical fabric of the global fiber optic network, a system of cables that spans continents and ocean floors, connecting facilities to each other and to the wider world. Terrestrial fiber runs follow the routes of roads, railways, and other infrastructure corridors, buried in conduit that protects the cables from physical damage. Undersea cables, some of the most remarkable pieces of infrastructure in the modern world, rest on the ocean floor in trenches and along routes that have been surveyed and carefully chosen to minimize risks from seismic activity, fishing operations, and other potential hazards. A transoceanic fiber cable contains within its armored outer jacket a small bundle of glass fibers so thin and optically perfect that a signal launched into one end will emerge thousands of miles away at the other end of the cable. The physics of this transmission are extraordinary. Light pulses generated by lasers at one end of the cable travel through the glass fiber, bouncing along the interior by a process called total internal reflection, losing energy as they travel, but periodically boosted by amplifier stations built into the cable at intervals. A single fiber pair in a modern undersea cable can carry tens of terabits of data per second, and a single cable may contain dozens of such fiber pairs, bringing its total capacity to levels that would have seemed impossible even a decade ago. The systems that monitor and manage all of this infrastructure, both inside individual facilities and across global networks, are among the most sophisticated operational environments in the technology world. The network operations centers of major facilities are the nerve centers of the entire system. These spaces are designed for continuous, around-the-clock operation. Large display arrays show real-time status information for thousands of monitored parameters. Individual engineer workstations provide access to detailed system information, configuration interfaces, and alerting systems. The engineers who staff these operations centers work in shifts that keep the facility under human supervision at every hour of every day. The monitoring systems they oversee generate vast quantities of data about the operational state of the infrastructure. Temperature readings from sensors distributed throughout the server halls. Power consumption metrics from every branch circuit in the facility. Network traffic volumes and quality measurements from across the entire switching fabric. Security system status from every access point. Generator fuel levels. UPS battery charge states. Cooling system performance parameters. Most of this monitoring data flows through automated analysis systems that apply threshold-based alerting and, increasingly, more sophisticated analytical approaches to identify anomalies and predict potential failures before they occur. The goal is always to move from reactive to proactive operations, to identify a component that is trending toward failure and replace it during a planned maintenance window, rather than waiting for it to fail unexpectedly and cause an unplanned service disruption. This philosophy of proactive maintenance is embedded in the operational culture of major facilities. Maintenance schedules are rigorous and documented. Every component in the facility has an expected service life and a replacement schedule. The redundancy built into the facility's design means that most maintenance activities can be performed without any interruption to running services. A faulty power supply in a server can be swapped while the server continues to run on its remaining power supplies. A failing network switch can be replaced, while traffic is redistributed to alternate paths by the routing protocols. The hardware lifecycle in a data center is relentless. Computing hardware ages and is replaced on regular cycles. What was state-of-the-art processor hardware 3 years ago may already be obsolete from a performance per watt perspective compared to more recent generations. Facilities are continuously cycling through generations of hardware, retiring older equipment, installing newer components, reconfiguring rack layouts, updating cooling designs to accommodate changing heat densities. The physical space of a data center is never truly static. It is always in a state of managed evolution. Retiring hardware presents its own set of challenges and requirements. The storage devices that have held customer data must be sanitized before they can be released from the facility. The process of data sanitization, overwriting storage media multiple times with random patterns, or for the most sensitive applications, physically destroying the media, is governed by strict protocols and documented with records that demonstrate compliance. The physical disposition of retired hardware follows environmental regulations governing electronic waste and materials recycling. The automation systems that assist with data center operations have become increasingly sophisticated. In the most advanced facilities, robotic systems assist with physical tasks that would otherwise require constant human presence on the server floor. Automated tape library systems manage the physical movement of tape cartridges used for cold storage and backup archiving. In some facilities, robotic systems capable of navigating the server aisles can identify, retrieve, and return hardware components without direct human intervention in the server environment itself. These automation systems do not eliminate the need for human expertise. They change its nature. The engineers who design, implement, and maintain automated operation systems require deep knowledge of both the automation technology and the physical infrastructure it manages. The maintenance of robotic systems is itself a specialized discipline, and the management of the software systems that coordinate automated operations requires skills at the intersection of systems administration, software engineering, and deep domain expertise in data center operations. The role of software in managing physical infrastructure has grown continuously over the decades. What was once managed through direct physical intervention, connecting cables, configuring hardware through local console interfaces, manually tracking inventory and capacity, is now managed through comprehensive software platforms that abstract the complexity of the physical layer into operational interfaces that can be managed remotely and at scale. Software-defined networking has transformed the way internal network configurations are managed. Instead of making changes to network configurations by connecting to individual switches and routers, network engineers work with centralized management platforms that translate high-level policy decisions into the specific configurations required across thousands of individual network devices. Changes that once required hours of careful manual work can now be applied at scale in minutes, with automated verification that the resulting configuration matches the intended design. The convergence of physical infrastructure management and software-defined operations is visible at every level of the data center. Power distribution units, the strips that distribute power to individual servers within a rack, are now instrumented and remotely controllable. Environmental sensors generate continuous data streams that feed analytics platforms. Every piece of hardware in the facility is tracked in inventory management systems that know not just what hardware exists, but where it is physically located, what it is connected to, what it is running, and how it is performing. Cybersecurity within the data center environment operates across multiple simultaneous dimensions. The physical security systems we have already considered, fences, access controls, biometric readers, surveillance, represent the outermost layer. But inside the physical boundary, an equally complex security architecture governs the digital environment. Network security begins at the perimeter of the facility's internet connections, where traffic filtering systems examine incoming data flows for signs of malicious traffic patterns. The volumes involved are enormous. Major facilities process millions of network connections per second, and identifying malicious traffic within that volume requires automated systems capable of analyzing traffic patterns faster than any human monitoring could accomplish. Distributed denial of service attacks, attempts to overwhelm facility network connections with artificial traffic floods generated from large numbers of compromised systems worldwide, are a routine concern for major internet-connected facilities. The defensive systems that handle these attacks have become highly sophisticated, capable of absorbing and filtering traffic volumes that would have seemed impossible even a decade ago. Within the facility network, security architecture follows the principle of least privilege. Systems and users are granted access to only the resources they actually need to perform their functions, and no more. Segmentation divides the network into zones that limit the ability of a compromised system in one zone to reach systems in other zones. Encryption protects data in transit between systems, even within the internal network where physical access is controlled. Logging and monitoring systems record every significant network event, creating audit trails that can be analyzed to investigate security incidents and identify the techniques used in any intrusion attempts. The operations personnel who manage security in these environments work in continuous rotation. Security operations centers operate 24 hours a day, monitoring for indicators of compromise and responding to alerts generated by automated systems. Incident response procedures are documented, rehearsed, and regularly updated based on emerging threat intelligence. The adversarial landscape is constantly evolving, and the defensive posture of major facilities must evolve to match. One of the least visible but most important aspects of data center security is the supply chain for hardware components. The hardware installed in major facilities comes from a global ecosystem of manufacturers and component suppliers. Ensuring the integrity of that hardware, verifying that components have not been modified or compromised before installation, is a concern that has received increasing attention as the stakes of supply chain integrity have become clearer. Advanced facilities employ inspection procedures and provenance verification processes that extend well beyond what ordinary commercial procurement would involve. The computing workloads running across the hardware in these facilities represent an extraordinary diversity of purposes and scales. A single physical server in a hyperscale facility might be simultaneously running dozens or hundreds of separate virtual machines, each one a logically isolated computing environment with its own operating system, software stack, and data. The virtualization technology that makes this possible is one of the foundational technologies of cloud computing, allowing the physical resources of the data center to be divided and allocated with great flexibility. A cloud computing platform operated from facilities like these provides customers with access to computing resources that they never need to physically provision or manage. A business that needs to run a large database application can request the necessary computing resources through a software interface and have them available within minutes, without purchasing any hardware, without visiting any data center, and without any need to understand the physical infrastructure that underlies the service. The complexity of the physical layer, the servers, the networking, the power systems, the cooling, is entirely abstracted away. From the customer's perspective, they simply have access to whatever computing capacity they have paid for. This model of computing, where resources are consumed as a service rather than owned as physical assets, has fundamentally changed the economics of information technology for organizations of every scale. Small businesses can now access computing resources that match or exceed what large enterprises could afford to own and operate just a decade ago. Research institutions can provision enormous computing clusters for specific projects and release those resources when the work is done. Media companies can scale their streaming infrastructure to match exactly the demand at any given moment, expanding during peak viewing periods and contracting when demand subsides. The physical infrastructure that makes this flexibility possible has to support extreme variability in load. At any given moment, the demand on a cloud computing platform can shift rapidly as customers scale their workloads up or down, as traffic patterns change with time zones, as major events create sudden spikes in demand for specific services. The hardware infrastructure is always operating somewhere between its minimum and maximum capacity, and the software systems managing workload placement work continuously to distribute that load across the available hardware in ways that optimize performance, minimize energy waste, and maintain the reliability guarantees that customers depend on. The energy consumption of large data centers is one of the most significant aspects of their operation, both economically and environmentally. A major facility consuming several hundred megawatts of power around the clock is spending enormous sums on electricity, costs that represent a substantial portion of the total cost of operating the facility. The pressure to reduce energy consumption while maintaining or improving computing performance is constant and has driven significant advances in efficiency over the years. The metric most commonly used to measure the energy efficiency of a data center is called power usage effectiveness, or PUE. This number is calculated by dividing the total power consumed by the facility by the power consumed exclusively by the computing hardware. A PUE of 1.0 would represent perfect efficiency. Every watt of power consumed by the facility going directly to computing work, with nothing spent on cooling, lighting, or other infrastructure. In practice, that ideal is unachievable, but the best designed modern facilities operate with PUE values approaching 1.1 or even lower, meaning that for every 10 watts used for computing, only 1 additional watt is consumed by facility infrastructure. Earlier generation facilities commonly had PUE values of 2 or higher. The improvements in efficiency achieved over the past 2 decades represent genuine engineering progress. Advanced cooling architectures, more efficient hardware, better airflow management, improvements in power conversion efficiency, and the adoption of economizer systems have all contributed to driving PUE values lower. The economic incentives are powerful. For a facility spending tens of millions of dollars per year on electricity, even small improvements in efficiency translate to significant cost reductions. The environmental dimension of data center energy consumption involves questions about the sources of the electricity being consumed. Major facility operators have made substantial commitments to matching their electricity consumption with power generated from renewable sources. These commitments take different forms. Some operators have invested directly in the construction of wind, solar, or hydroelectric generation facilities. Others have entered into long-term power purchase agreements that fund the development of new renewable generation capacity. Still others participate in renewable energy certificate programs that create financial linkages between their consumption and the production of renewable power. The commitment to renewable energy matching has become a genuine driver of renewable energy development in certain regions. A major facility operator announcing a long-term renewable energy commitment in a region where wind or solar development is viable can provide the financial certainty that enables the construction of new generation capacity that would not otherwise have been built. The scale of the commitment, hundreds of megawatts of continuous consumption, is large enough to support substantial generation projects. The water consumption of data center cooling systems is another environmental consideration that has received increasing attention. Cooling tower systems that use evaporation to dissipate heat consume significant quantities of water. In water-scarce regions, this consumption can be a genuine concern. The data center industry has responded by developing closed-loop cooling systems that minimize evaporative water consumption and by siting new facilities in regions where water resources are more abundant. The development of air cooling and liquid cooling technologies that avoid evaporative water consumption entirely is also motivated in part by these environmental considerations. The future of data center infrastructure is being shaped by a combination of continuing demand growth, technological evolution, and the increasing environmental and regulatory context in which major facilities operate. Several trends are clear enough in their direction to examine with confidence. The density of computing hardware per unit of floor area will continue to increase. The newest generations of processors and accelerator hardware are more powerful than their predecessors, and that power comes with higher heat output per unit of floor space. Facilities designed for the hardware densities of the next decade will require cooling infrastructure capable of handling heat loads that would overwhelm the systems common in facilities built even a few years ago. The shift toward liquid cooling in all its forms, from rear door heat exchangers to direct liquid cooling to full immersion, will accelerate as air cooling approaches its physical limits. The hardware architectures dedicated to high-performance computing workloads are evolving rapidly. Processors and accelerators optimized for the kinds of computations involved in training and running large-scale models are among the most power-hungry hardware deployed in data centers today. Individual accelerator units consume hundreds of watts, and the systems built around them, containing dozens or hundreds of accelerators interconnected by high-bandwidth fabrics, can push rack power densities to levels that require dedicated high-power electrical infrastructure and purpose-built cooling systems. The interconnect infrastructure within and between facilities is also evolving. As the workloads running in data centers become more distributed and more latency sensitive, the quality and capacity of the network connections linking different parts of the infrastructure become increasingly important. New networking technologies offering higher bandwidth, lower latency, and more flexible traffic management are being deployed in facilities that operate at the frontier of the industry. The physical connections between facilities, both the terrestrial fiber infrastructure and the undersea cables spanning ocean basins, are being continuously expanded to support the growth in traffic. Automation will play an increasing role in both the operation of physical infrastructure and the management of computing workloads. The complexity of modern data center environments is already beyond what manual management approaches can handle at scale. Automated systems now handle routine operational tasks that once required direct human intervention. As the technology for automation and autonomous operation matures, the scope of what can be managed automatically will expand, allowing human expertise to be applied to higher level decisions and to the design and improvement of the automated systems themselves. The geographic distribution of data center capacity is evolving as well. The early concentration of major facilities in a small number of metropolitan regions has given way to a more distributed pattern, as operators have recognized the advantages of placing capacity closer to the populations and industries being served. Lower network latency, better compliance with data residency requirements, and reduced dependence on long-distance network connections have all driven the construction of facilities in a wider range of geographic locations. This trend toward more distributed infrastructure is expected to continue. Edge computing facilities, smaller installations positioned at or near the locations where data is generated and consumed, represent one of the most active areas of data center development. Unlike the massive hyperscale campuses that are the focus of much of this discussion, edge facilities may be compact installations occupying a room rather than an entire building. They serve the requirement for computation to happen very close to its source, enabling applications where the round-trip delay to a distant large facility would create unacceptable performance degradation. Industrial automation systems, autonomous transportation infrastructure, real-time medical monitoring, and interactive entertainment applications are among the use cases that drive demand for edge computing capability. The relationship between large centralized facilities and distributed edge installations is not a simple replacement dynamic. Both scales of infrastructure will coexist, each serving the requirements best suited to its characteristics. The large centralized facilities offer economies of scale, the most advanced infrastructure, and the ability to aggregate massive workloads that require the computational density only achievable at very large scale. The distributed edge facilities offer proximity, reduced latency, and the ability to serve applications where centralized processing is not viable. The challenge and opportunity for the industry lies in building the software and networking systems that allow these different tiers of infrastructure to work together seamlessly. The human expertise required to design, build, and operate this infrastructure is among the most valuable in the technology industry. The disciplines involved span structural engineering, electrical engineering, mechanical engineering, network engineering, software engineering, operations management, security, and more. The integration of these disciplines in the construction and operation of major facilities requires teams of specialists who understand not just their own fields, but enough of the adjacent disciplines to collaborate effectively. The physical construction of a major hyperscale facility involves thousands of workers over a period of months or years. The structural systems, electrical infrastructure, mechanical systems, and network cabling all require specialized installation teams working in coordination. The commissioning of a new facility, the process of systematically verifying that every system works correctly and that all systems work correctly together, is a massive undertaking in its own right, requiring careful sequencing and testing before any customer workloads are introduced. The operational staffing of a running facility includes the engineers who manage day-to-day operations from the Network Operations Center, the technicians who perform physical maintenance activities in the server halls, the security personnel who manage access control and surveillance, the facilities engineering teams who maintain the cooling, power, and structural systems, and the management layers that coordinate all of these functions. At a large campus, the total staff directly employed in operations may number in the hundreds, supported by specialized contractors who are called in for specific maintenance activities or system upgrades. The facilities themselves are in a constant state of managed change. New server hardware is installed on a continuous cycle. Network configurations are updated to accommodate new services and changing traffic patterns. Cooling system adjustments are made as the heat load distribution across the floor evolves. Power infrastructure is upgraded to support higher densities. The building systems that control lighting, access, environmental monitoring, and facility management are updated and expanded. A data center that looked a certain way when it opened will look significantly different 5 years later, not because it has been replaced, but because it has been continuously evolved. Standing inside one of these facilities, beneath the rows of blinking servers, within the roar of the cooling systems, beside the racks of fiber connections blinking with traffic, it is possible to appreciate something about the nature of the modern technological world that is easy to overlook in the abstracted experience of using a digital service through a screen. The convenience and capability of modern digital life rests on a foundation that is profoundly physical. Glass fibers in ocean trenches, diesel engines waiting in sealed rooms, battery banks occupying entire corridors, cooling towers exhaling warm air into open sky, water circulating through hundreds of miles of insulated piping, concrete and steel structures built to precise specifications to support the enormous weight of thousands of server racks. The information age has often been described as something immaterial, a world of bits and signals, of software and data, of virtual environments and digital interactions. And from the perspective of the user experience, that description has a kind of truth. But beneath every digital experience, at some level of the system, there is always metal and glass, heat and electricity, moving parts and human attention. The infrastructure we have been examining is not a detail of the digital world. It is its physical reality. The scale of investment required to build and operate this infrastructure is extraordinary. The largest hyperscale campus projects represent capital expenditures measured in billions. The cost of the land, the construction of the buildings, the procurement of the electrical infrastructure, the installation of the cooling systems, the purchase of the server hardware, the build-out of the network connections. Each of these represents a substantial investment, and together they add up to sums that place major data center construction among the largest infrastructure projects in the private sector. The continued growth in this investment is not a sign of excess, but of necessity. The demand for computing resources, storage capacity, and network bandwidth grows with every passing year, and the pace of that growth shows no sign of slowing. Every new device connected to the global network adds to the aggregate demand on the infrastructure. Every new digital service introduced adds workloads. Every organization that transitions from physical to digital operations shifts its computing requirements to the infrastructure of the cloud. Every new application that generates or consumes data in ways that require significant processing adds to the load. The facilities we have explored in this examination are not simply buildings that happen to contain computers. They are the physical substrate of a networked civilization, the infrastructure upon which modern economies, communication systems, medical capabilities, educational resources, and an ever-expanding range of human activities depend. Their continued operation is assumed by billions of people who have no particular awareness of their existence. Their failure, even briefly, would reverberate through systems that span the entire globe. The engineers and operators who keep these facilities running carry a weight of responsibility that is proportional to the dependence placed upon their work. The redundancy systems, the monitoring, the maintenance protocols, the security measures, the testing programs, all of these are expressions of a professional commitment to reliability that is sustained across continuous cycles of human attention, year after year, without respite. Long after the visitors have left and the loading docks have fallen quiet, the facilities continue their unbroken operation. The servers process their requests. The cooling systems maintain their temperatures. The generators wait in readiness. The network switches move their traffic. The battery arrays hold their charge. The fiber runs carry their light. The monitoring systems watch their parameters. Somewhere beneath the surface of a northern ocean, a fiber cable carries billions of simultaneous conversations between continents. Somewhere in a desert, cooling towers exhale the heat of 1 million computing processes into the dry night air. Somewhere in an industrial park, indistinguishable from its neighbors, behind fences and cameras and locked doors, the invisible machinery of the digital world performs its endless essential work. The lights blink, the fans turn, the signals travel at the speed of light through glass, so pure it would be invisible to you if you held it up to the sun. And the world, connected and dependent and largely unaware, goes about its business, carried, unbeknownst to most of its inhabitants, on the shoulders of these extraordinary machines.